Stoichiometry. We would have to pick big words, wouldn't they? Well, when you see the ending of a word is has metry or metric in it, that just means to measure. Stoichio refers to anything that's countable. So we're counting things, measuring them that way. It refers to the way that we determine the amount of something, the number of. All right, I'm muddying the waters. Let me just get on with it. Stoichiometry, the extended definition, is the way quantities of materials that go into a reaction, we can determine the products that come out, how much of the products. So we've got to have a way of writing a balanced equation so that we can keep track of the elements and compounds that go in and the elements and compounds that come out. If we can do that and balance it so that we're not creating mass and we're not destroying mass, okay, we have to obey that law, then we should be able to calculate with a given amount of reactants, how much product will we have? That's essentially stoichiometry. You can read that at your leisure on the recording. The problem is, now we understand. Initially, chemical reactions were only described in terms of masses of reactants producing masses of product. And that was not the whole story. That didn't tell you what was actually going on the microscopic level. And by the mid-1860s, universities and companies, particularly in Europe, were running into problems with their reactions. They were losing money because when a reaction went wrong, they didn't know how to fix it. What they needed to know was that it wasn't the mass that was reacting, it was individual atoms and molecules that were reacting. Okay. So what we need is a way to count the atoms and molecules in a reaction, but we can't see them. We can't actually count them. Well, we could now, but it's inefficient. We have the technology now that we can count atoms and molecules, but not relative to the types of reactions that we're interested in, and not for cheap either. So a method was devised called counting by weighing. And what that says is that if you can weigh something, and you know an average weight for so many of the objects, then if you weigh it, then you can expand that to the total number of objects that are in your sample. That's where dimensional analysis comes in. When we did conversion factors, we weren't just spinning our wheels learning how to do that. Okay, I've already said atoms are too small to count. The other thing that we have to assume when we're going to do this counting by weighing, is that all the objects in the sample that we're going to count are identical. Now we know they're not, so we have to think of an average object. That'll make more sense in a few minutes. In order to do this now, what we have to be able to do is calculate the average mass of one of the objects. So if you know the mass of one of the objects and you know the mass of the sample, you can use that that value as a conversion factor. Okay, we're going to do some examples in a minute. For instance, if I have a pile of marbles that weighs 39.80 grams, let me keep up with this, so I'll see if it, yeah, the math is actually here. We have a pile of marbles. We know that whole pile weighs a certain amount, 394.80 grams. And we also know that 10 marbles weigh 37.6 grams. How many marbles are in the pile? Well, we need an average mass for one marble. And all we have to do is take this mass and divide it by 10. That's the average mass of the marble. Okay. So let's do it this way, the way that I've taught you to do it up to this point. 394.80 grams. We're going to convert that, use a conversion factor to give us the number of marbles. Okay, so our conversion factor cancels the grams. That's the numerator, that's the denominator. And in the numerator, we have marbles. So we cancel this, and that leaves us that. So we have one marble is 3.76 grams. That's why this one says divide that into it, because that's essentially what we're doing here. But I think this makes more sense because it shows you the process of using a conversion factor. So if we divide 3.76 into that value, we get 105 marbles. Now, do you think we actually have 105 marbles in that mix? Yeah, probably pretty close. But there's no guarantee. Remember, with that number, these two are certain and that one's uncertain. Okay, so and with every measurement, there is always error. Always, forever. So we're saying that this calculation gives us 105 marbles, but it could be 106, it could be 104. We just have to accept the possibility of error. So how do we count the number of atoms in a pile when the atom is too small to weigh? Right? This was fairly simple because we could actually take 10 marbles, weigh them, and get our conversion factor. So we need a conversion factor for atoms. So I got my eraser. All right, so here's what we have to do. We have to arbitrarily establish a mass unit for a single atom. And we try to pick an atom that is easy to isolate. And that's in terms of isotopes also. Because we know that different isotopes of the elements have different masses. So we have to pick a specific isotope of an element and fix, at least for that element, fix a value. And then everything else is referenced to that one. Okay. As it turns out, we're fixing that isotope of carbon, carbon-12. And we're saying that it has, for one atom, 12 atomic mass units. Okay, that's the only one that has infinite zeros. It's an exact number for carbon-12. Carbon's easy to come by. Right? All you have to do is burn anything that's living and separate the carbon from the ash, and then separate the carbon isotopes. I mean, it's not a simple process, but it's easier than it would be for other elements. Okay, so that's our standard. There's reference here to Avogadro's law, right? And I'm not going to invoke Avogadro's law just yet. But did I give you Avogadro's law yet? Don't recall it? Okay. Well, that's okay. We'll get to it. Okay, so there's our standard. The authors, the creators of this slide set use little u for atomic mass units. I like AMU because if you're not careful, you could mistake that for something else. You could even mistake it for the Greek letter, like that, which means something else. It means micro, doesn't it? Micro prefix. Anyway, that's our standard. Everything else is referenced to that one. Okay. Now, this is approximately, since it's 12 nucleons, protons and neutrons, and we know that protons and neutrons are at different masses each. So what we're saying is that even if they do vary, what comes out to be carbon 12, which is equal to what? Number of protons plus number of neutrons. That even with their variability, the difference between these two, we're going to fix it at 12. We just have to arbitrarily say that's 12 atomic mass units and go from there. And then as we determine the masses of other elements like oxygen and nitrogen and whatever else, oh, gold, don't forget gold. Then once you determine those, but their values are not going to be whole numbers. They'll never be whole numbers in this scenario. Now, they will have whole numbers up here, right? Because of the way this is calculated. It's protons plus neutrons. So this will always be a whole number for every element. But this value for each atom is going to be different because it's referenced to that value. Okay, so that's not going to help us much in chemistry because we can't isolate the isotopes before we do a reaction. We have to deal with a natural mixture of carbon isotopes. Now, this isotope itself is almost all of the carbon, 98.9% of all carbon. But there's enough of carbon-13 with some value here, which will not be, which will have a decimals, has a value here. And then there's carbon-14, but we don't count it first, primarily because it's like 0.01%, plus it's always decaying, right? It's radioactive. So we're just going to use carbon-13 and carbon-12 to determine an average mass for a carbon atom. That way, we don't have to deal with isotopes when we're doing chemistry. Okay. And there's carbon-14, but we're not going to use it. All right. So, have I described, I haven't done it yet. I'm thinking about other courses and teaching. This average atomic mass is kind of like determining your grade point average. It's a weighted average. So courses that have 3 or 4 credit hours to them are weighted heavier for the grade you get in that course than one where you maybe take 1 or 2 hours for the course. Okay. All right. So how do we do it? Well, we take the contribution of 12 atomic mass units is this value, and this value for the carbon 13, which is 13.0034, right? Because it's referenced to this one. And we don't use percent times these because this is parts per hundred. The fractional equivalent is the way we multiply it times 12 here, rather than that. This tells us, yeah, if you have 100 of these altogether, 98.89% of them are going to be carbon 12. But that doesn't help us for calculation. We'd have to divide that whole thing through by 100. So instead, we use this fractional value, 0.9889 times 12 and 0.0111, which is the fractional equivalent of that percentage. Then we add those together. Okay, let me see. No, it doesn't do that. So let's do that. Just for this one. So what would that first calculation be? 0.9889 times 12 is 1.08. That's not right. I did it wrong. Hold a second. 0.9889 enter 12. There we go. That's 11.8668. Atomic mass units is contributed by the abundance of carbon 12. And then 0.0111 times 13.0034 is only contributing this much. Atomic mass units to the total. So then when we add them together, we get 12.01. I rounded off to 2 places there. That's the average atomic mass for carbon with its naturally occurring abundance of carbon 12 and carbon 13 isotopes. So we can work with that. Now we don't care the isotopes that are in the mix when we're working with carbon, because they're chemically the same anyway. Okay. All right. Now, what's the probability that you're going to find in a sample of carbon? If you have isolated pure carbon, what's the probability that you're going to find any one of those atoms with a mass of 12.01 atomic mass units? Answer: 0. There will not be a single atom in that mix that has that mass. That's a weighted average of the total group. Okay. And since we don't work with single atoms, then the average mass is useful. Okay. This is just a picture of how we separate the isotopes. Okay. We won't spend a lot of time on it. This is a mass spectrometer. This is one type of mass spectrometer. It's a magnetic sector mass spectrometer, one of the earliest types. Now they use something that's a little cheaper to manufacture and more compact. They use you probably used a quadrupole in yours. But it separates the isotopes based upon their mass. When you charge the atom, make it a single charge, and then accelerate it through an electric field, and then hit it with this magnetic field, the force is based upon the charge. So the force against the carbon 12 is the same as the force against the carbon 13. But since carbon 12 is lighter, it bends more because it's the same force, but the heavier isotope doesn't feel as much push because it's heavier. So they separate. and you can detect them out here. And the electronics in our equipment now is fast enough, you can count individual strikes, which is equivalent to an atom. Okay, so here we have an example of an element consisting of 62.6% of an isotope with mass 186,956 and 37.4% of another isotope, which is a little lighter, 184.953 atomic mass units. What's the average atomic mass for that? You would take 0.626 and yeah, okay. Here we go. You take 0.626 times this value here, and then 0.374 times this value, and then add them together. That's the weighted averaging. And we get a value that's 186.20. Right? What element is that? Well, we know that if we have the mass, the atomic number, the number of protons, it's easy. Right? We just look for that number. Here on this chart is in red. But we don't have that. What we have is an average mass for that element. And fortunately, you can follow along, and you see also as these get bigger, the average atomic masses get bigger too. So you just follow along and see if we can find one that's unique, 186.2. So here we go. And then we look on this side, it's a little smaller, and this side is a little bigger, so we've kind of bracketed in at RE, rhenium. Okay. So there's more than one way to determine an element. If you know the number of protons, which is rare, then you can do that. It's more likely that you would know the average atomic mass. And you can usually find it up here. There are a couple of places on here where the masses get really close together. And then you probably need a tiebreaker then.
How did you get 186 with the answer and added the 186 from the top to the 182 on the bottom?
Oh, you have to multiply by this fraction first. 0.626 times that value, and then 0.374 times that value, then add them together. Yeah, if you just add them straight together, you can have like 370. That'll never do. I skipped a math step in there. That's what happened. Okay. So we've entertained the concept of average atomic mass in terms of what's the average atom in a mix of isotopes. What does it weigh? So we've determined so many atomic mass units, and that's what each one of these values is. Right? They're all fractionals. Even carbon is a fractional because it's a mix of isotopes. The only one that is an exact number is carbon-12. So naturally, the current carbon is also going to have a fractional value for its atomic mass units. But those don't help us much for doing calculations in chemistry, right? Because we don't deal with just one average atom at a time. But it's a good place to start. Now what we need to do is get a handle on doing chemistry with lots of atoms, billions of atoms at once. So that's something we can actually weigh on a balance. If you have billions, trillions of atoms in a sample, then it'll show up as a mass on your balance. So we need a relationship between mass and numbers of atoms. And that bridge is called the mole. The mole is simply a number of things. Now, it's tied to reality, right? But we don't have time to go into that. People that spend their whole lives refining the value for a mole. But for us, this is good enough. That's a mole of things. It could be a mole of atoms, mole of ions, it could be a mole of molecules. It could be a mole of chickens. It doesn't matter. It's just a number of things. Now, by definition, it's tied also to this carbon-12 isotope. So what it says is that for this carbon-12 isotope, if you have 12 grams of that isotope, exactly 12 grams of that isotope, you will have this many atoms. That many atoms of carbon-12 equals 12 grams. Okay. So by defining it that way, now these values also are not just atomic mass units per atom, but they're also grams per mole of the naturally occurring mix. Now we can work with that. All right, that's called Avogadro's number. Avogadro didn't come up with it. He's just honored. They honored him with putting his name with it because it's his theory that made this possible. That's a lengthy story and I'm already eating up too much time, so I'm going to have to pass on it. Okay, now, like I said before, if you have a mole or that many atoms of naturally occurring carbon, you won't have 12 grams because you're going to have some carbon-13 mixed in there. So if you have a mole of naturally occurring atoms, you will have that many grams. Okay, so now look what we've got. 12.01 grams of carbon per mole for 1 mole. It looks like a conversion factor, doesn't it? And that's how we use it. 1 gram of carbon equals 1 mole. And we use anyone on that table that we want, that we need as a conversion factor like that. You just substitute the value here for the different elements and move on with it. Okay. So how about calculating the number of iron atoms in 4.48 moles? Let me check the hard copy, see if I have to write it. No. It's here. So, like any dimensional analysis problem, we start off with what's given, 4.48 moles. And then we use our conversion factor because this many atoms per mole. So this is in the denominator, this is in the numerator, and they cancel. And now we're left with this number times that number, and the units now are atoms of iron. So in 4.48 moles of iron, we have 2.70 times 10 to the 24th iron atoms. Okay. That's what's known as molar mass, the mass of a mole. The molar mass of nitrogen off of that table is 14.01. And I usually just round off 2 decimal places. That's good enough for our work. Okay. What do we do if we've got a compound though? Say we have a mole of water molecules. So we have 6.022 times 10 to the 23rd water molecules. right? If we have 1 mole of those, then we have 6.022 times 10 to the 23rd of this formula. How many oxygen atoms does that represent? 1 mole. Right? If you got one of these, you got one of those. So 1 mole, 1 mole. But if you got 1 mole of these, you've got 2 hydrogen atoms for each mole of the total. That means you have 2 moles of hydrogen in that unit. So if we're going to calculate the molar mass, or how much does 1 mole of water weigh, all we have to do is add the molar mass for that one and 2 times the molar mass of hydrogen. Okay, so round it off. That's 16 grams per mole for oxygen. Look at that. And for hydrogen, it's 2 times 1.01. Added together, that's the molar mass of water. Okay. And even if it's a massive molecule like this one, barium nitrate, you just follow the same procedure. How many moles of each one of the atoms do you possess if you have a mole of the formula unit? Okay. Since this is not a molecule, right? It's an ionic compound, it's a formula unit. So we've got 1 mole of barium. For every mole of barium nitrate, we have 1 mole of barium. There it is right there. We just left out the per mole here. We also have 2 nitrogens. Notice that bracket. This is a polyatomic ion. So if you have 2 of these nitrates, you've got 2 moles of nitrogen. There. And we have 6 moles of oxygen. Right there. Multiply and add them up. And molar mass of barium nitrate is 261.35 grams per mole of that formula unit. That's why it's important, why I stressed learning how to write compounds, because you're going to have to do that in order to do this calculation. If the word problem says barium nitrate reacts with something, if you don't know how to write that formula, you're stuck. You will never be able to calculate this if you cannot write that formula. Okay. All right, which of the following is closest to the average mass of 1 atom of copper? This is kind of a stupid slide, right? There's no atom of copper that's going to weigh grams, right? It's too small. So logically is this one. But you can do the calculation. You start, this is a chain to conversion. 1 copper atom. We start with 1 copper atom when we convert it to moles of copper atom. So 1 mole of copper per 6.022 times 10 to the 23rd copper atoms. So that cancels the copper atoms and leaves us with moles. Now we have need of the molar mass of copper. So we can cancel the moles and leave us with grams of copper. And that grams of copper, that molar mass, came right off the periodic table. Right, so we're canceling units and we're left with that many grams for each copper atom. The review document will give you lots of practice doing this. And then work problems. If you come out with the wrong answer, you can't figure out why, you can go to the work problems and see how I did it and say, oh yeah, that's where my mistake is. How about the number of copper atoms in 63.55 gram sample of copper? Kind of a trick question. 63.55 gram sample of copper is 1 mole. So you have 1 mole of atoms, or 6.022 times 10 to the 23rd. All right. What am I doing next time? We're out of time. What may happen is when it comes time for lab, I have to stop. I can't go into lab today because we have some work to do. So what I'll do is after lab is over, I'll come back in here and finish the lecture if I run short. So if we have 100-gram samples, each one of these, let's see, magnesium, zinc, and silver, we got 100 grams of each one. Okay, which one contains the greatest number of atoms? Think about it this way. How many atoms does it take to make a gram of each one? If you got the heaviest one, it'll take fewer atoms, right? The lightest one will take most number of atoms because you need more of them to make up that mass. So what we want for the greatest number of atoms is the lightest element. Which one has the smallest molar mass? And we look on a periodic table and we find that magnesium. Magnesium has the smallest mass. So it'll take, that requires more atoms to make 100 grams. Okay. Just logically, without doing the calculations. Okay. I'm gonna have to rearrange them because they're in different order on this slide. So if A is 107.9 grams of silver, and B is 70 grams of zinc, and this one is 21.0 grams of magnesium, put them in order from greatest to least number of atoms. So the greatest, well, they're not all the same mass now. So we've got to at least estimate the number of moles in order to compare them. Okay. 107.9 grams of silver. How many moles is that? There's silver. 107. That's 1 mole. Okay. How about 70 grams of zinc? Zinc, 70 grams. That's more than a mole. Just a little over a mole. And 21 grams of magnesium, 24.3 grams is a mole. So this is less than a mole. Now we put them in order. Right? From greatest to least. This is greatest. And this is least. And this one's in the middle. Okay. I like these markers. They erase really well. So how about 100-gram samples of each of the following? Rank them in order of greatest to least number of oxygen atoms. All right. So here I said time for Henry Ford. Set up an assembly line because you're going to do the same operation on each one over and over again, exactly the same way. You just change some parts. So if we do it like this, we have water, dinitrogen monoxide, C3H6O2. I think that's propionic acid, and CO2. We have 100-gram samples of each. We're doing the same thing over and over again. We're going to do unit conversions. To convert them into the number of oxygen atoms. Now, do we actually have to convert them to Avogadro's number of atoms? If we're going to do comparisons, all we need is numbers of something, which means moles. If we can find the moles for each one, then we don't have to go to those big numbers, those huge powers of 10. But first of all, we got to convert them to moles of compound. Then if we know how many moles of water molecules, then we can use a factor to say, all right, if it's moles of water molecules, that's the same as the number of oxygen atoms, because it's 1 to 1. One of these for every one of those. One of these for every one of those. 2 oxygens for every one. 2 oxygens for every one. So it's a 2-step process. Well, we need to get rid of grams and leave us with moles. So what's the magic number? It's a different number for each one. Right? We determined this one already, 18.02 per mole. Dinitrogen monoxide, how about that one? Nitrogen is 14.01, so that's 28.02 plus 16. For oxygen. That's 4402. This one takes a little more work. 3 carbons at 12.01. Did that for carbon times 3. And then 6 times 1.01 for hydrogen. And then 2 oxygens plus 2 times 16. 32. All right, 74.09. And then carbon dioxide. So we got 1 carbon, 12.01. And again, 32 for oxygens is 44.01. Okay. That gives us the number of moles of compound. Now we can convert there's 1 mole of oxygen for every 1 mole of compound. Same here. Here we have 2 moles of oxygen for every 1 mole of compound. And here we also have 2 moles of oxygen for every 1 mole of compound. So those cancel. And that leaves us with moles of oxygen. Then we can rank them. So 100 divided by 18.02. Is 5.55. This is in moles. Oh, by the way, why did I write it MOL and not MOLE? Because MOL is the abbreviation for MOLE. Seems like a little effort for nothing, right? A lot of effort for nothing. 100 divided by 4402. .27 moles of oxygen. And 100 divided by 74.09, 1.35. Okay, and the last one, 44.01, 2.27, 2.27. Oh, you know what I forgot to do? Nobody caught me. I didn't multiply by 2. 4.54. And 2.70. Okay, now we have moles of oxygen. Moles of oxygen. That many grams of each of these samples. So what's the order? From greatest to least. Here's the greatest. That's number 1. This is number 2. This is number 3, and this is number 4. Okay. That's Henry Ford. Assembly line. Same thing over and over again. How do we solve problems? We won't spend a lot of time on this because you learn by doing. First of all, you ask the question. What is the question? Right? Without the question, there's no answer. Then you have to devise a plan of getting there. With what you have, you're given, usually in a test question or homework problem. How do you get from what you're given to the answer? Devise a scheme. Sometimes it's a simple calculation, just bam, bam, bam. Sometimes you have to bust it apart into separate operations and then bring the answers from there back together. And then do a reality check. Is your answer reasonable? Right. And that'll vary from each problem. What seems reasonable? Right. If you work a problem and you're trying to calculate, how much calcium carbonate to weigh out on the balance to do an experiment, and you do your calculation, it turns out to be 3 metric tons. You may want to go back and look at your work again. All right. Okay. So what we're getting into now, believe me, we're headed for stoichiometry. We need these skills under our belt before we can do anything with them. Mass percent of an element. Where we're headed with this is experimentally determining the molecular formula of a compound. This is where we start. When a chemist goes into the lab, used to be, wet bench chemist would take a new compound, be sure it's pure, and then analyze it for its elemental composition. And usually come out with a mass percent value for each element. And this is the way it's expressed. A mass percent of each element is the mass of the element in the compound divided by the mass of the compound. And you can work that 2 ways. You can actually go in the lab and do it, just ratio the masses. Or if you want to know what it is and you already know the compound formula, then you can calculate the mass percent from the formula. Right? So for this one, iron 3 oxide, Fe2O3, how do we calculate the mass percent of iron in that compound? Well, assume you have 1 mole of a compound. That's key. If you have 1 mole, then you can calculate how many grams that mole represents. So the total for a mole of iron 3 oxide is going to be the sum, just like we did before, the sum of this mass, 2 times iron, 3 times oxygen, and there it is right there. That's the total for a mole. But within that mole, you have how much iron? Well, you only have 2 irons. So notice that iron is going to be in the numerator and the denominator. And in the denominator, it's going to have everything else. So once you ratio those and times 100, you get 69.94%. With that formula, that's the mass percent of iron in that compound. Blank faces. So if we don't have time to set this up again, but if we take those same set of compounds and we run the mass percent calculation, just like we did for iron 3 oxide, then you will get a percentage of oxygen in each one of these compounds. And then you can rank them just like we did for the number of moles of oxygen. Only now it's a different determination. You're doing mass percent of oxygen. But if you set it up just like Henry Ford, just do it the same way over and over again with different formulas this time, just like we did on the previous slide. Okay. Mass percent is our gateway. First, we're determining the empirical formula for a compound. The empirical formula is not the molecular formula. The empirical formula is the simplest whole number ratio of atoms in the compound. So here's the illustration of that one. If you have benzene, C6H6, and you have acetylene, those are two different compounds, but they will have exactly the same empirical formula. The whole number ratio of this one is for every 1 carbon, you have 1 hydrogen. For every 2 carbons, you have 2 hydrogens. So the ratio, the simplest whole number ratio, cannot be reduced any further, is 1 to 1. This one also is 1 to 1. Okay? So you're probably asking yourself, well, what good is that? You can determine the empirical formula of your compound, but it could be any one of 100 different compounds. You're kind of stuck, right? Okay, we're on our way. We go to the empirical formula first. Notice that if we have a multiplier out here, like that, and propagate it through our sample, this would be 6 to 6, and this would be 2 to 2. Okay? So where we're headed is, we want to find out that number right there. Once we determine this, then we want to go to the next step and determine what is that multiplier. And that will give us our molecular formula. It's a two-step process. All right. Oh, we didn't do the calculation yet. Yeah, I probably got time to do this one slide. And then I'll have to come back and finish. Because we're going to do that. And then we're going to learn how to balance equations. Yeah, that's the last thing we're going to do in this chapter is balance equations. And in fact, one of the handouts is this little helpful hints on balancing equations. Right? So I need to explain that. And I know I'm going to have to do it in the video later. So let's determine the empirical formula for this compound. Notice that we're given mass percent of each of the elements in the compound, carbon, hydrogen, and oxygen. And with that information, we can determine the empirical formula. Here's how you do it. Henry Ford. We have carbon, that's 49.3%. By mass, we have hydrogen, that's 6.9% by mass. And we have oxygen, that's 43.8% by mass. So what does percent mean? It means parts per 100. So if we're talking about mass percent, we're talking about 49.3 grams per 100 grams of total mass. That's the key, because we cannot convert percent to moles. And in order to find the empirical formula, the ratio is moles of atoms, numbers of atoms, not masses. Okay, when we see a formula with subscripts, that's numbers of atoms of each one in that formula unit. So we have to convert this to moles in order to get that ratio, right? So we assume 100 gram sample. If we assume 100 grams, that means this is 49.3 grams of carbon. This is 6.9 grams of hydrogen and 43.8 grams of oxygen. Now we can convert it to moles. This is grams on the bottom to cancel, moles on the top. Okay, so how's carbon? 12.01. Hydrogen is 1.01, and oxygen is 16. Okay. So all we have to do now is find out what is the ratio of these. 49.3 divided by 12.01. That's 4.10. Okay. And 6.9 divided by 1.01 is 6.83. Moles of each of the elements. 43.8 divided by 16. 2.74. Okay. Are we done? No. Because we don't have fractional atoms in our formula. We need whole numbers. The simplest way to get whole numbers out of that list, now this ratio is established. For every 2.74 moles of oxygen, you have 6.83 moles of hydrogen and 4.10 moles of carbon. That ratio is fixed. So anything we do to multiply or divide by any one of these, if we do it to each one of them, then we maintain the ratio. So the simplest way is divide everything through by the smallest one. This is obviously 1. 6.83 divided by 2.74 is 2.49. And 4.10 divided by 274. Let's see. 2.74 is 1.50. Okay, we're getting closer, getting warm. Can we multiply these by any value that will make all of them whole numbers? In this case, we have to sort of get close, like darts and hand grenades and atom bombs. If we multiply this one by 2, that should get rid of that 0.5, right? This is very close to 0.5. So if we multiply by 2, it gets rid of that half and makes a whole number. There's another half. So if we multiply by 2, or think of it this way, this is 1.5, this is 2.5, and that's 1. So if we multiply by 2, that gets rid of these halves and leaves us with whole numbers. So by 2, now we move this out. This is 3. This is 2.5 is close enough to 5, and this one's 2. So that's why C3H5O2, C3H5O2 is the empirical formula. That's the simplest whole number ratio of carbon, hydrogen, oxygen. It's not necessarily the molecular formula. What we're looking for is this multiplier.
So why don't you divide by 2.74?
Where?
But divide by the smallest.
Yeah, right here. What I'm trying to do is get us to closer to whole numbers. So if I divide each one, the ratio is already established. That's fixed. Moles, moles, moles. So if I do something, if I multiply or divide by the same number of every one of these, the ratio is maintained. So if I divide by 2.74, that makes this 1, that makes this something else and something else. We're edging our way toward finding whole number ratio. We're down to a fractional, like 2.5, 3, and 1.5, and 1. So if I multiply now by 2, that makes this one 3, that one 5, and this one 2. But we need this multiplier. So here's the way we find that. This formula has an empirical molar mass. If we add these together like we did before, say 3 times 12.01 and then 5 times 1.01, add that on, and then 32 for the oxygens, 2 times 16. This empirical mass is 73.08 grams per mole of formula unit. So here's where that extra bit of information comes in. The molar mass of the compound is actually 146 grams per mole. And you have to determine that by some other method. You can do elemental analysis and get a mass percent fairly easily. But you need another way to get this value. Okay. And we're going to take a look at those. It's called colligative properties. We get to colligative. We haven't talked about those yet. Okay. Colligative properties. That's where you can determine the number of moles of a solute in a solution, and it doesn't matter what the solute's made of. That's good, because we want to know what the molar mass of the substance is. The true molar mass is that value. Well, if this is 73.08, it can't be 1 times that. This can't be 1, right? 1's wrong. How about 2? 2 times 73 is about 146, isn't it? Okay. So if we use 2 for X, then it's C6H10O4. And you can calculate it yourself, right? Calculate this molar mass, and it should be 146. That's how we go from percent composition by mass to empirical formula, and then make the jump from empirical to molecular formula. This is the actual formula. Okay. I got 8 minutes. Let's see. Okay, when we write a chemical reaction, I'm going to use as much time as I can. When we write a chemical reaction, there's a standard format. Left to right. Reactants on the left, products on the right with an arrow in between. And we're going to find out later that we're showing that the reaction going from this side to that side. But in reality, it can go both directions. Just keep that in the back of your head. And this reaction is balanced. How do we know it's balanced? Because the number of atoms of each one, or the number of moles of each one, is the same on both sides. So 2 times 3 is 6. We got 6 moles of oxygen here, but there's another one right there. So that's 7. So here we have 2 times 2 is 4. 3 times 1 is 3. So that's 7. So if you count them up, you have the same number of atoms of each element on either side of the reaction. That's how you know it's balanced. Okay. You can look at this in terms of atoms and molecules or moles. And the key to that understanding is what is the coefficient? The coefficient here is 1. So 1 molecule of this ethanol plus 3 molecules of oxygen. And remember, oxygen is diatomic. There's one of those in the blue squares. 3 moles of oxygen plus 1 mole of ethanol yields 2 moles of carbon dioxide and 3 moles of water. Or you can think of them in terms of molecules too. Right? 1 molecule of that plus 3 of those yields 2 molecules of that plus 3 of those. But for calculation purposes, moles is more useful. The coefficient stands for how many of these before you get to the next operator sign. And if there's not a number out there, it's always 1. We don't write the 1, that's redundant. Just remember that when we write a balanced equation, reactants, yields, products, that's overall, right? This is what we start with, this is what we end up with. And the arrow is kind of like a black box. There's a whole lot of stuff going on there. But we're only interested at this point in the macroscopic results. It goes in this way and it comes out that way, and what happens in between, we don't care right now. But that comes in the second semester. We talk about equilibrium, chemical kinetics, and reaction mechanisms. Baby steps. Okay. So these are I just put these steps up here, 1, 2, 3 on down, and they came, they didn't come off that document. No, sorry. Just so that they would be in print, but really understanding how to do it takes practice. Your book, most chemistry books say, you write out your compounds and your elements in the reactant side and the product side. Most of the time they're given to you. And then you balance them by inspection. If your book says balance by inspection, that's because the authors don't want to bother with teaching you how to balance equations. They're leaving that up to the instructors. So I've got a method, and call it my budget method. And it's good to start with, and we modify it later as needed. But it keeps track of all the atoms on both the reactant and the product side. So as you proceed, you readjust your budget, you recalculate your budget, and by the time you get to the end, you know instantly whether your equation is balanced or not. I have to show you one in order to, I don't have time now, there's only 3 minutes left. And these are the helpful hints that are in that document. So they're right there. And this is not a step-by-step. These are just things to be mindful of, and some of them are useful in some situations and some in others. Okay. Next thing we want to do is to learn how to balance an equation. And I've got an animation here that shows you step by step, but I think it'll make more sense if I take that equation and put it on the board and show you my method up there. So let me see if I can squeeze all this information into the space allowed. Ammonium phosphate. Let's see, let me write it here. Ammonium, oops, right, ammonium phosphate. And I'm going to leave the phases out. These things right here, just to conserve space. It's not necessary to balance this equation. Sometimes you need to know it. But in this case, we don't need it. So I'm going to leave it out just to conserve space. So I'm going to write it like this, and then I'm going to leave a gap here for coefficients. And then calcium phosphate, 2 of these, and then ammonium chloride. And you can see that. Okay. So the first thing you do is inventory your elements and polyatomics. The reason I say that is the elements are obvious. You want to know the number of elements on either side of the equation to start with, your beginning point. But one of the helpful hints that I give you is that if you have polyatomic ions in the reactants and you've got the same polyatomics in the products and they don't break up in the process, right? The reaction does not split that polyatomic apart, right? It stays together. You can use that polyatomic as a balancing unit, and it saves you a whole lot of headache. So that's why the first one in here is ammonium. Okay. The next one is phosphate. All right, this is plus and this is 3 minus. And the phosphate stays the same on both sides. So we can use it as a balancing unit. Then the next one we come to is calcium. And actually, you don't have to write the charges on it because we're only balancing the element, the atoms, or the polyatomics. And the charges at this point don't matter. Then we have chlorine. So does that cover everything? Yeah. Ammonia on both sides, phosphate on both sides, calcium on both sides, and chlorine on both sides. Okay, so we've got our inventory set up here. On this side, how many of these ammonias do we have? We have 3. How many phosphates? Just 1. 1 calcium and 2 chlorines. This is your beginning inventory. On this side, we have 1 ammonia. So right off, you can see that it's not balanced. We got 3 on that side and 1 on that side. Phosphate on this side is 2. Calcium is 3 on this side. And chlorine is 1 on that side. And that's our beginning inventory. Let's see. Okay, there's 3. There's 1. There's 1. There's 2. Okay. 1 on that side. All right. So the question now is, where do you start? And to balance an equation, you start with the correct compounds written. So this is the correct way to write ammonium phosphate. Ammonia has 1 plus charge, phosphate has a 3 minus charge, so it takes 3 pluses to balance the 3 minuses. That's why I made such a big deal about writing equations, compounds, writing compounds from their names correctly. Is because you're going to need to know that to do this. This one has a calcium with a 2 plus charge and 2 chlorines with a minus charge each. So 2 minuses balances a 2 plus. Once you've written the reactants and products this way, and you do your initial inventory, then you have to decide, where do I start? Well, with experience, doing a lot of these, you may be able to see the best place to start. But if you don't, then just start at the top. Eventually, you will get to the end with a balanced equation. It just may take you longer. Also, remember that the only way that you can balance an equation is with coefficients. Once you have written these compounds correctly, you can't touch them. You cannot mess with the subscripts anymore. They are sacred. You have to put coefficients in front of each one of these compounds in order to balance it. So let's start with calcium. You got 3 calciums on that side. We need 3 on this side. So we put a 3 coefficient. Okay. Now we recheck our inventory. Now we have 3 calciums. And we have 6 chlorides. Okay. I think that's what we've done here. Yeah. Now we're going to balance the chlorines. We got 6 on this side. Now we need 6 chlorines on this side. Okay. So that gives us 6 here, but it also gives us 6 ammonias. Okay. And you can see what we're building up toward is a balancing of the numbers on both sides. These are both the same. These are both the same. This one now is up to 6. We need 6 on this side. So how do you get 6 ammonias out of that compound? You need a 2 here. 2 times 3 is 6. But we also have to multiply that times this. That means 2 phosphates. And as it turns out, that procedure has balanced the entire equation, and you can see that it's balanced readily by the comparison of these numbers, 6, 2, 3, 6. That equation is balanced. You don't have to go back in and recalculate to see, okay, we got 6 ammonias here. Do we have 6 over here? Oh yeah, we got 6. With this budget method, you can see instantly that your equation is balanced. All right. Okay. I'm going to erase this one now. The budget method is good for probably 80 to 85% of the equations that you'll encounter. And of course, all of the equations you'll encounter for this upcoming exams. So, with the correct coefficients, what we have is the smallest whole number ratio of coefficients across that equation. If this equation is balanced, and it's not balanced because we have an oxygen there and 2 oxygens here, a calcium there and 2 calciums there. So which one would balance it? At this point in our development of our skill set, we want the smallest whole number ratios. So this one would be the smallest whole number ratio for balancing that equation. But technically, the ratio of 2 to 5 to 2 to 1 is the same as 4 to 10 to 4 to 2. But this can be reduced further, just divided by 2. Divide that by 2, divide that by 2, by 2, by 2, and you get this equation. So if that's possible, if you can divide and get a whole number, divide everything by the same number and get a whole number in front of your coefficients, then you should do it. So if you end up with this one, you should reduce it to this one. And at this point, we don't have any fractional coefficients either. We don't use fractions here. Now in the future, We'll find situations where we do need to write fractional coefficients, but that comes later. Right now, we're at the very beginning, and the rule is whole number coefficients, smallest whole number ratio of coefficients. Okay. Just a reminder, which of the following is true concerning balanced chemical equations? Well, the number of molecules is conserved? No. The number of molecules can be wildly different. So that first one is false. Oh, okay. The second one, coefficients tell you how much mass of each substance you have. No, they tell you the numbers of molecules that you have, the numbers of atoms that you have in the reactants and the products. The atoms are neither created nor destroyed. That is true. That's the essence of balancing an equation. You preserve the number of atoms of each element on the reactant side for the product side. The coefficients indicate mass ratios? No. Number ratios. And the sum of the coefficients on the reactant side equals the sum of the coefficients on the product side? No, not necessarily. They don't have to. If they do, it's purely coincidence. This is the only statement that's true out of all of those 5 statements. This is just a reminder. The number of atoms of each element on both sides of the equation have to be equal. The subscripts of your compounds cannot be changed to balance an equation. Once you have correctly written the compounds, then you cannot touch the subscripts. The balanced equation tells us the ratio of the number of molecules which react and are produced in a chemical reaction. Right? And it'll be different for each reaction. Coefficients can be fractions, but for now, they should be given the lowest integer multiples. Smallest whole number ratios is our goal for now. All right. Now we can go, once we've learned how to balance equations, we can go to stoichiometric calculations. And anytime you have masses of reactants going in and you want to find out what mass comes out, you always start with correctly written compounds and then a correctly balanced equation. If you don't have both of those, then you cannot do stoichiometry. So, if the equation is written in terms of numbers of atoms and numbers of molecules, how do we get masses out of that? We get masses out of that by molar mass. And I'll show you an example here coming up. This is like before. These are just the steps that you would follow to do a stoichiometric calculation. And I've got them up there just so that they'll be recorded. This is a flow chart. I don't particularly care for the flow chart, but some of my students do like to have these flow charts around, so I put that up there for you. Okay, so here's an example. And this equation looks to be balanced. Let's write it up on the board and check it, see if it's balanced. So we have P4, that's a solid, plus 5 oxygens, that's a gas, yields 2 P2O5 solid. Okay, now we can check to see if it's balanced. Say, okay, 4 phosphorus atoms, 4 phosphorus, 2 times 2 is 4. 5 times 2 is 10, 5 times 2 is 10 oxygens. So yes, this equation is balanced. So we don't have to do that. Now, what's the question? if 6.25 grams of phosphorus, 6.25 grams of phosphorus is burned, what mass of oxygen does it combine with? So the question is, how many grams of oxygen are required to consume all of that phosphorus using this reaction? Okay. The next rule, after you have a balanced equation, the next rule is you cannot move anywhere in that equation unless you're in moles. You have to be moles or you're stuck where you are. So this grams, we're stuck. We can't move. We can't say anything about that one in terms of its mass because this is mass, we cannot move. We have to convert it to moles. Think of it as a great divide there. Mass can't get through it. Only moles can get over or under or through that barrier. So if we have 6.25 grams of P4, our conversion factor needs to cancel grams and leave us with moles. So what's the magic number? The molar mass of P4. So we look at our periodic table and find out what phosphorus weighs. 30.97. 30.97 grams per mole, but that's for one phosphorus. We need 4 of them. So we multiply 4 times that. Get my calculator out. So 30.97, 4 times. I get 123.88. Now, first thing you notice is I've got more significant figures down here than I do up there. But this is going to be a conversion factor, so it doesn't matter. Because conversion factors are exact numbers. 123.88. So the grams cancel, divide this one into that value, 6.25, divide that number into it, and I get 5.045 times 10 to the minus 2 moles. That's moles of P4. Okay? So that means, and I'm going to have to erase this because I don't have enough room. Now we have moles of P4. This is 5.045 times 10 to the minus 2 moles of P4. Now we can move. We can find out how many moles of oxygen are required because the ratios are in terms of numbers of atoms, numbers of molecules, moles of molecules. So with this, we need another conversion factor. And we get this conversion factor from the balanced equation. This is moles of P4 here to cancel that one. And then we want moles of O2. So what's the ratio? It's 5 to 1. 5 to 1. That's how we get a conversion factor out of a balanced equation. This will cancel moles of P4, and 5 times that value is 2.523 times 10 to the minus 1 moles of oxygen. So now we know how many moles of oxygen it takes to completely consume 6.25 grams of P4. But the question was mass. So now that we've made it over here using moles, we have to convert back to grams. So this mole is going to be converted to grams using the molar mass of oxygen. Right? one oxygen atom is 16 grams per mole, two oxygens is 32. 32 grams per mole. So 32 times that value gives us 8.07 grams of oxygen. That's what's required. That much mass of oxygen is required to consume 6.25 grams of P4 in this balanced equation. Okay? That's one type of stoichiometry, where you start with mass and you move somewhere in your equation and end up with mass. But the only way to get there is to go through moles. Now, this balanced equation, we could just as easily, once we find the moles of this, we could have converted to that and determined if the question had asked how much P2O5 is produced. Then we could do the calculation and adjust this number of moles that was determined here, and instead use 2 moles of that per mole of this, 2 times that, few moles, and then use the molar mass of this to convert to mass. Okay? That's how you do it. Okay. So now on this slide, what we have is we've gone from sublime to ridiculous. And I'll explain myself in just a second. I want to check something out here. Okay. So I've got a series of slides here, so I don't have to write all this stuff on the board. Here's the question. You start off with methane reacting with oxygen in air to produce carbon dioxide and water. That's what we just did in the lab. The Bunsen burner was taking natural gas, which is predominantly methane, and combining oxygen with air and producing carbon dioxide and water. The other reaction, the companion reaction, this is a separate reaction from that one. This is ammonia burning in oxygen to produce nitrogen monoxide and water. So the first thing you have to do is what? Well, these are given right here. But what we have to do is complete the reaction and balance the equation. So let's do that first. So if we have methane and reacts with oxygen to produce carbon dioxide and water, right? We set up our budget. Yeah, let's go ahead and do the budget. We'll do this one first, and then we'll do the ammonia. So we've got carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen. Okay. So how many carbons do we have? 1. We have 4 hydrogens and 2 oxygens. On this side, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. Okay. Now, for this reaction, we'll use one of my hints. One of my hints on that document I handed out is if you have a single element as a reactant or a product, save it to last. Save this one to last for good reason. Because when you add a subscript, a coefficient, when you put a coefficient out here, it only changes oxygen. Remember when we put a coefficient here, here, or here, it changes both of those elements. But when you put one here, it only changes that one. So we save that one to last. Because if that's the last step, then we're done. Okay, so we're not going to touch the oxygens right now. Suppose, and the carbons are all right. Right? So what if we do hydrogens? Right? If we put a 2 over here, that means 4 hydrogens, and it also means 2 plus 2 or 4 oxygens. Correct? Now we got that balance, that balance. Now we can balance this oxygen on that side with the 2. So we're balanced. That's the first equation. We haven't even gotten to the real question yet. We have to balance the equations first. So let's put the other one up here now. Ammonia plus oxygen yields what? Nitrogen monoxide and water. Okay, let's do our inventory. Nitrogens, hydrogens, oxygens. Nitrogen, hydrogen, oxygen. We got 1 nitrogen, 3 hydrogens, 2 oxygens. Got 1 nitrogen, 2 hydrogens, and 2 oxygens. Okay. Let's see here. It looks like this is the only one that's out of balance, the hydrogens. But notice we've got a 3 on this side and a 2 on that side. So we got a hydrogen here and hydrogen there. One of those hints that I gave you in this document says, if you have the same element in a single compound on one side and then a different compound on the other side, but they're odd and even, then try cross multiplying. Here's what I mean by that. If this one's, if this is 2 hydrogens and this is 3 hydrogens, put that 2 over here and that 3 over here. Okay, let's see what that does for us. Now we've got 2 nitrogens, we have 6 hydrogens, oxygens are unchanged here. On this side we have 6 hydrogens and 4 oxygens. Okay. Now we've got 2 nitrogens here. We need 2 nitrogens there. And that changes the oxygens to 2 plus 3 is 5. 5 oxygens. So now the nitrogens are balanced, the hydrogens are balanced, but the oxygens are not balanced. Time for another hint or a trick. We've got this one sitting here by itself. We want to make 5 on this side. So how do you get 5 over here? You can't get 5 out of a whole number times an even number. Anytime you multiply 2 times a number, you always get an even number. So here's what we're going to do. We're going to use the fraction trick. If we say, let me move this over a little bit. If we say 5 halves of an oxygen molecule gives you 5 oxygens. Correct? Look at it this way. There's your oxygen, there's your oxygen, there's your oxygen, there's your oxygen, and there's your oxygen. You got 5 oxygen molecules here, 5. But you're going to take half of them. So we're only going to take half of these. 1, 2, 3, 4, 5. 5. Okay, that's the fraction trick. Now that we've got it balanced, we got 5, 5, 6, 6, 2, 2. We want to get rid of that fraction because we don't want any fractions in our coefficients. It's balanced right now, undoubtedly. But what we want to do now is get rid of that fraction. And the best way to get rid of a 2 in a fraction is to multiply that fraction times 2, right? Because what? 5 halves times a 2. 2's cancel and you're left with 5. So you do the whole equation multiplied by 2. So 2 times 2 is 4. 2 times 5 halves is 5. 2 times 2 is 4. And 2 times 3 is 6. Okay? So now we have that balanced with the smallest whole numbers. I'm going to clean it up now. So let's take this out here like that, put a 4 here. Let's take this out, put a 5. Take this out, put a 4. Take this out, put a 6. There we go. So now we have 2 balanced equations. That's the first step. Let's go to the next slide. Oops. Go to the next slide. All right, that's balanced. See, this is balanced. Yep, that one's balanced. Now the question is, with these balanced equations, what mass of ammonia would produce the same amount of water as 1 gram of methane? So the mass of this one and the mass of that one, or the moles. It just says the same amount. So it could be mass or moles, doesn't matter. But if we have 1 gram of methane, how many grams of ammonia will give us exactly the same amount as of water from either reaction? And we're also saying that this is excess. So the amount of oxygen doesn't matter. You've got as much oxygen as you need to completely consume that and completely consume this. So what's the connection between these 2 equations? It's the amount of water. So what we need to do is find out how many moles of water will 1 gram of methane produce. That's our first goal. Okay, we got the balanced equations there. All right. So remember, we can't move anywhere in that equation unless we have moles. So we got to convert grams of methane to moles of methane. That's what this one does right here. That's the molar mass of methane. And it tells us that we have 6.23 times 10 to the minus 2 moles of methane. Moles of methane. Okay. Now we want to convert that to moles of water. So what's our conversion factor? Well, we've got a coefficient of 1 here and a coefficient of 2 there. So that means we have, and in standard notation, 0.1246 moles of water produced by burning 1 gram of methane. And the question was, this has to be the same amount as that, right? So this would be 0.1246 moles of water. Now, how do we convert water to ammonia? We use conversion factors, the ratio of 6 to 4. So 0.1246 moles of water converted to ammonia, right? Water here, ammonia here. So we have 6 waters and 4 ammonias. So 2/3 of that value will be the moles of ammonia. 8.31 times 10 to the minus 2 moles of ammonia. How do we convert that to mass? Because that's the final answer. What's the mass of ammonia? We use the molar mass of ammonia to convert moles now to grams. And there it is, 17.04 grams per mole is the molar mass of ammonia. That allows us to convert moles of ammonia back to grams of ammonia, and the value is 1.42 grams. What that means is if you burn 1.42 grams of ammonia in excess oxygen, you get exactly the same amount of water as a product as when you burn 1 gram of methane in excess oxygen. Okay? Now, another concept. Up to this point, we haven't been too interested in whether or not the exact amounts of reactants are present so that they all consume and you end up with products only. That's called a stoichiometric mixture, stoichiometric reaction. In real life, that never happens. Because if you're trying to measure out your reactants to get exactly the right amount of mass of each reactant, there's always error in your measurements. You'll either measure out just a hair too much or a hair too little. And this concept, the limiting reactant, helps us manage that problem. So in practical terms, the limiting reactant is the one that runs out first. It's less than stoichiometric. It will run out first. That's the one that limits. When it runs out, the reaction stops. Can't go any further. You may have some leftover reactants of the others in the mix, but that one limiting reactant is completely gone. Okay, this is an idea of a stoichiometric mixture for this reaction. N2 plus 3H2 yields 2 ammonias. That's the Haber-Bosch reaction. It was originally invented by Fritz Haber, just prior to World War I. See, the Allies were using strategic advantage to strangle Germany. Germany needed nitrates to make their explosives and their gunpowders and whatever. And they couldn't get it because the major source of nitrates was Chile in South America. So we were blockading them so they couldn't get their nitrates. In fact, it was bird guano, bird crap that built up on the coast of Chile over centuries, and it was hundreds of feet deep. So they would mine that stuff, and it's come out, it's mostly sodium nitrate. So Fritz Haber set his mind to the task of creating nitrates that his country needed. And the first step in that process was to figure out how to take nitrogen gas from the atmosphere, combine it with hydrogen gas, principally produced from methane, and make ammonia. If you can make ammonia, then all you have to do is oxidize it and you can make nitrates. Okay, so this is the Fritz, and Haber came along and refined it afterwards. All right, this stoichiometric mixture says that if you have exactly the right amount of nitrogen here and exactly the right amount of hydrogen here, they will all react and produce ammonia only. 2, 2, 2, 2, 2, just like that, 2. 3, 3 here, 1, 1 there. That's a stoichiometric mixture that I said earlier never happens, but it's where we start. What usually happens is one of the reactants is limiting. And in this slide, the limiting reactant is hydrogen. Notice that when we pair them up in the reactant side, we have enough hydrogen for that nitrogen, enough for that one, and enough for that one. These two are left out. There's no hydrogen for those guys. So when the reaction is completed, You get ammonia, but you also get some extra hydrogen, nitrogen left over. So the one that ran out was hydrogen. That is the limiting reactant. Okay. So the point of this slide is to use this balanced equation for hydrogen reacting with oxygen to make water. And if I haven't said it before, that's the same reaction that fuels many of our modern rockets. Liquid hydrogen, liquid oxygen in separate tanks brought together in the engine, and they're turned into a gas before you get there. And when you ignite them, you get lots of energy back. Well, this balanced equation can be read as moles of hydrogen and moles of oxygen. So look at the following reactions and which one could produce the greatest amount of product. Okay, 2 moles of hydrogen and 2 moles of oxygen, right? 2 moles of hydrogen need only 1 mole of oxygen. So hydrogen is limiting. That means hydrogen runs out. That's the end of the reaction. And 2 moles of hydrogen will make 2 moles of water. Right? Oops. So the first one, A, let's see, let me erase this because that might be confusing. A produces 2 moles of water. How about B? 2 moles of hydrogen and 3 moles of oxygen. You're in the same boat. Hydrogen is limiting. You got too much oxygen. You only need 1 mole of oxygen. So this one runs out and produces 2 moles of water. How about C? 2 moles of hydrogen and 1 mole of oxygen produces 2 moles of water. This is the stoichiometric mixture. Okay. 3 moles of hydrogen and 1 mole of oxygen. Now, which one is limiting? Oxygen. You got 1 mole of oxygen and 3 moles of hydrogen, and you only need 2. So oxygen is limiting. 1 mole of oxygen produces 2 moles of water. And E. Each produces the same amount of product. Notice that when we have identified a limiting reactant, and there can only be 1 limiting reactant, then all the other reactants are excess. We have 1 limiting reactant and many excess reactants. Okay? All right. So the point of this slide is to get at when we actually have a new balanced equation that we've just created, and we're given amounts of reactants. How do we know which one is limiting? Right? Suppose it's given to you in mass. You've got to convert to moles. So in order to tell which one is limiting, you look to the product. How much product can be produced by either one? If all of, say A and B react to produce C. What if we use up all of A to make C? Then that'll be the amount of C due to A. And if we use up all of B, we say B is excess. And then we say A is excess. Then we have C that can be produced from B. The one that's limiting is the smallest one. So if C from A is less than C from B, then A is the limiting reactant. All right. Now there are going to be several problems in the review document for you to work out these scenarios. And we'll look at those in detail on the review day. But for now, there's another fly in the ointment. It's called percent yield. We started off with a stoichiometric equation, one in which all of the reactant is exactly enough to react with all of the other reactant to make product, and no reactants are left over. The other problem, then we introduced limiting reactants. The other problem is that due to reaction inefficiencies and just handling the products, you never get 100% of the expected yield. It's always less than 100%. If you get more than 100%, then there's a calculation error probably. Or a reaction that either the reaction is happening that you did not predict, or your product is not purified so that you have contaminants in it. And you think that you have more than you do. That would give you more than 100% recovery. So that the yield, the percent yield is written like this. The actual yield that you get for a product divided by the theoretical yield. So the theoretical yield is the one that you calculate and that we've been doing up to this point. So the actual yield is you measure it and compare it to the theoretical yield. Okay, so here we have a reaction of P4. This will start to wear out in a second. P4 plus 6F2 yields 4PF3. And that equation is balanced. And this marker is going dead on me. So let me see if I got one in here that I can use. Okay. That's a balanced equation, correctly written. What mass of P4 is needed to produce 85 grams of PF3? 85 grams. Actual yield. Actual. If the reaction has a 64.9% yield, with a 64.9% yield. Okay. So if we're going to do a calculation and find out what mass of this is required, we can't use that value because this is the value after we've lost some of it. So in order to make sure that we have that much after we've lost some of it, we've got to calculate what is the theoretical value for this one. All right, so we go back to our equation. The actual divided by the theoretical times 100. And in this case, it's equal to 64.9%. So we know what the actual is. It's 85 grams. So let's put that in here. 85 grams. Now we have an equation in one unknown. We can solve for it. So how do we solve for this one? Well, the theoretical, let's get this one over on that side, right? This is multiply, this is divide, so we can move that on in the denominator here, it'll be the numerator there. So theoretical is on this side now, and over here we have 85.0 times 100 divided by 64.9. And the theoretical yield now will be, after I calculate, 85 divided by 64.9 times 100 is 130.97. It's 130.97 grams of PF3. That goes into this equation here. But remember, we can't move in that equation when we're in mass. We have to be moles. So now I have to convert that to moles. So let's do this, make some room. 130.97 grams PF3. We need to know the molar mass of PF3. Right? Whenever you have grams and moles in a quotient, think molar mass. So phosphorus is 30.97. And fluorine is 19.0. 19.0 times 3. And then add those together. And I get 87.97. There we go. So if I multiply, if I divide this one into that value, I get 1.489 moles of PF3. Now we can convert, right? PF3 in the bottom and P4 in the top. What's the ratio? 4 here and 1 there. So divide 4 into that one, right? This cancels, and leaves us with P4. So I get 0.3722 moles of P4 and convert it to grams. Right? What's the molar mass of P4? Well, 30.97 times 4. 123.88 times that value is 46.1 grams of P4. That's how you do it with percent yield as a factor. Okay, there are all the calculations that I did on the board, and they're splattered up there for you. Okay, I think this is the last slide. I hope it is. Yep, that's it. So practice those calculations. If you have any trouble, you can't figure it out, go to the worked problems, that handwritten worked problems, see if that will help you. If that doesn't do it, then call me or meet me on my office hours.